Hello, welcome to another Cosmology talk. Today we have Hironao Miyatake, who is an associate professor at KMI at Nagoya University. He's speaking today about the just released joint analysis of the Subaru Hyper Suprime Cam Year 1 results and SDSS galaxy catalogs. I only saw this paper this morning because we're recording this before the paper has gone live. So I might not know all the cool parts of it yet, but there are certainly some interesting results, in particular fresh constraints on sigma 8 and omega matter. So there's something to say about the sigma 8 tension, which is the younger sibling of the two big lambda CDM tensions. And most interestingly, perhaps, the degeneracy direction of their constraints in the sigma 8 omega m plane appear to be different to both the CMB and other probes of the current matter density, which is interesting and cool. Yeah, before starting, I just want to say I'm excited to do this release of talk video at the same time more often, especially for observational groups. So if anyone has an interesting paper coming out soon, please get in touch. But enough from me. Let's hear from Hironao. Welcome. Congrats on getting the paper out. Do you want to tell us quickly what is described in the paper?
First of all, thank you very much for inviting me to the Cosmology talk. Yeah, this is a great opportunity to advertise our result. What we did is using the galaxy clustering and galaxy lensing signal. So using two probes, we can constrain cosmological parameters, and especially we focused on omega matter and sigma 8. So the combination of galaxy clustering and galaxy lensing. So this has been becoming, say, like a standard method, which has been used for DS and kids. So they released their results earlier, that we finally got our first result. So yeah, I'm very happy.
So if people were remembering this talk and your paper 6 months from now, and there were only two things that they could remember, what would you want those two things to be?
So we performed very reliable measurement. So we used the spectroscopic galaxy samples, and more specifically both galaxy samples as a tracer with a luminosity cut to make a volume limited sample. And also for source galaxies, we selected by the conservative redshift cut. So measurement itself is very reliable, we believe. And also another point is that to exploit the measurements down to small scales, we built a model using the so-called dark emulator. So this is emulating the two-point statistics out of n-body simulation. So without running the n-body simulations, so you can immediately get the two-point correlation functions in a nonlinear regime very precisely. And also we combine that the dark emulator prediction with analytical halo occupation distribution, which is called HOD, to model galaxies populating dark matter halos. So combining these two, we were able to use down to very small scales.
The next question I always ask is why you did this, and particularly why is it happening now and not a few years ago or a few years from now? I guess to some extent it's literally when the data is available and when it's finished being analyzed. But can you put it in perspective beyond that?
Right. So Subaru Hyper Suprime Cam. So it started at 2014, and we used the data up to 2016. So yeah, it took some time to get this paper out. Where after the observation up to the 2016, we had to make a galaxy shape catalog, which is used for the weak lensing analysis. So we had to do lots of validation. So it took, I think, 2 years. Yeah, that paper was out in 2018. And another thing is a modeling side. So this modeling side, I mean the modeling small scales, down to small scales of the lensing and clustering signal, was very challenging. And so we started constructing the emulator I mentioned. So there is an expert who developed that emulator, and then that paper was out in 2019. And then we also combined that dark emulator output with analytical HOD. And then we did a lot of tests using the mock signals. So that also took some time. Yeah, so anyway, yeah, it took years because we tried to be conservative for measurements. So we wanted to develop the model that can be applied to small scales. So this is a most time consuming part.
Have you gone to smaller scales than the dark energy survey in kids?
Yeah, yeah. That's why it took some time. But yeah, the gain was a lot. So
There's more data that HSC have taken. This result is on 100 and something square degrees, I guess, but then there's in total up to about 1,000.
We call this a year one sample, like this is 140 square degrees, and this is just 1/10 of full survey. So the more data will come soon. Well, actually, we already are done with constructing the year 3 galaxy shape catalog for weak lensing measurement. So that will about 450 square degrees. So yeah, that will be tripled.
So do you want to get into the details? How did you combine the two surveys? What do you mean by galaxy-galaxy lensing and galaxy-galaxy clustering, and what were the results?
Why we want to combine the galaxy-galaxy lensing and galaxy-galaxy clustering. So the matter correlation function of the delta m. So this is sensitive to cosmological parameters. And we, as I said, we focused on the omega matter and sigma 8 constraint in this paper. So this correlation function is on the figure on the right. And so this is like a correlation function of the orange point. So this is the simulation, N-body simulations. And all these orange points are dark matter particles. So if you can take a correlation between these dark matter particles, we can get omega matter and sigma 8 constraint immediately. But so as you know, like a dark matter cannot be directly observed by the telescope. So galaxies are often used as a tracer of the dark matter distribution. But as you may know, like galaxies are biased tracer of underlying matter distribution. So we can easily compute galaxy-galaxy clustering. This is a correlation function of the galaxy density fluctuations. But the problem is that, as I said, galaxies are the biased tracer. So it cannot be directly used to constrain cosmology. But at large scales, so you can approximate galaxy number density as a b times matter density fluctuations. And so this becomes psi gg is proportional to the b squared times psi mn. So b squared here is a linear bias parameter. So let me rephrase the problem. So we do not generally know the b, and then this b parameter degenerates with sigma 8 and omega matter. So that's why we cannot directly get the constraints on cosmological parameters by just looking at the galaxy-galaxy correlation function.
And I guess also B on small scales stops being this smooth linear thing.
Right. So that's why also some team limited themselves to the large scales because if you go to small scales, a linear bias approximation does not hold anymore.
And I guess also the value of B can depend on the type of galaxy. Like more massive galaxies have a bigger B and...
Right. That's true.
You were saying it's an approximation at large scales. I guess it's worth mentioning that there is theory backing that up, that if you talk about the peaks of a Gaussian field, then you expect them to have a linear bias compared to the field itself. So if the dark matter is a Gaussian field, then the galaxies that would form at the peaks would have a linear bias. Because I'm always suspicious whenever something this simple is being used, that hopefully there's some theory backing it up. And I guess on the large scales there is, but yeah, as you were saying, on the smaller scales.
Yes. So then, right, so galaxy correlation function, it's shown as like a correlation function in blue dots on the right figure. I put this as galaxies. But this bias parameter can be calculated by combining galaxy-galaxy lensing. On the bottom right figure, if there is a structure between us and distant galaxies, so distant galaxies are slightly distorted. And by measuring the distortion, we can reconstruct the foreground structure between us and distant galaxies.
Can I just point out something that might not be helping anyone, but when I was reading your paper this morning, it confused me for ages. When you write galaxy-galaxy lensing, it's not galaxy-galaxy lensing, it's galaxy with galaxy lensing. That's
galaxy with galaxy lensing, right? So one galaxy is a tracer, so this is a foreground galaxy, and the other galaxy is distant galaxies, which is called source galaxies, which is distorted by the tracing tracer. Galaxy-galaxy lensing is practically measuring the correlation between galaxy and the matter, because we are looking at the matter distribution around the galaxies. And then this is a cross correlation on the galaxy and matter, and then if you substitute the delta G equal B times delta M. So this becomes a B times xi mm. So this is just 1B. So galaxy-galaxy lensing is a B times xi mm, and the galaxy-galaxy clustering is a B squared times xi mm. So by combining these, we can break a degeneracy between a bias parameter and a cosmological parameter. This is the point of this method, which is usually called 2x2 point analysis. So yeah, this was proposed, I guess, like 15 years ago, not really 15 years ago, less than 15 years ago. And then firstly applied to SDSS data 2011, 12, 13-ish. It's now emerging as a standard method in recent 10 years, as well as a cosmic shear. So cosmic shear was really, how to say, like it has more history, right? It was firstly detected around 2000, and it has more than 20 years of history. So this probe is newer, but now it's becoming a standard. So yeah, KIDS and DS got the results out, and now the HSC got the first result out.
And the shear would be like, I guess, the equivalent of galaxy lensing, right? And then this is just adding additional data, or am I missing the point?
Yes. Autocorrelation of galaxy lensing. This is called cosmic shear. Yes. Yeah. This is another probe. It's also powerful. So it is more like the directly looking into this matter correlation function, rather than going through the galaxy things. But we have different systematics for each probes. Yeah. For example, in our configuration, we do not worry much about so-called intrinsic alignment. This is one of the big systematics in the cosmic shear analysis.
Oh, it's also just more data, right? Like it's independent data, so one should use it.
Yeah, right. So yeah, it's independent data, right? So let me introduce a Subaru HSC. So this is on the summit of Mauna Kea, Hawaii, and altitude is more than 4,000 meters. So it has a superb image quality, like a PSF is 0.6. So this helps us to measure the weak lensing, because we have to measure the teeny tiny distortion of galaxies. And then if the PSF is small, it's easier.
And PSF is point spread function, which is like if it was just a point, how wide it would look on the actual camera.
Yes, that's true. Right. So the SDSS is like 1.0, and KIDS is close to us, like a 0.7 or something. Yeah, and the field of view is very large. So on the bottom right picture, this photo shows the focal plane of the Hyper Suprime Cam, and it's covered by more than 100 CCDs. So you can see it's tied very tightly. And the field of view is 1.5 degree diameter. So it's 7 times full moon and 500 times Hubble Space Telescope. Another advantage of a Hyper Suprime Cam is it has a 8.2 meter primary mirror. So there are stage 3 surveys, so which includes KIDS and DS and HSC. So among them, also HSC has the largest mirror, 8.2 meter primary mirror. So this is equivalent to what LSSD does. So in terms of seeing on the primary mirror, we are doing something similar to LSSD, but the Subaru telescope itself is an open use telescope. So the time can be used for the HSC survey is kind of limited compared to the telescope dedicated to the survey like SDSS or LSSD. But our image is very similar to what LSSD would see. We are still shallower than them, but our data, our HSC data has been used for the LSSD software development. And actually, we are using the LSSD image reduction pipeline for the HSC. So yeah, this is a good testbed for LSSD. So yeah, this is a HSC survey, what the HSC survey looks like. And so we have 1,400 scale degrees down to limiting magnitude to 26. So this is much deeper than DS or KIDS. So they are like between 24 to 25. A wide layer, so it's shown as a dark red or wine red regions in this map. And we have 3 distinct fields. One overlaps with XMM on the left, and on the right, around the equator, it overlaps with Cosmos. And on the north, on the right, this overlaps with a hectomap, which is a spectral surveys of the clusters. We try to overlap with other major surveys like SDSS and BOSS, and also ACT, and also Viking, Gamma, VVDS.
So I guess ACT is a CMB telescope. Viking, I don't know of.
Yes, right. So the ACT is high resolution, high sensitivity CMB survey that can observe, of course, like a primary CMB down to the very small scales. And also, like, it's very sensitive to the secondary CMB effect, which includes Sunyaev Z-bridge effect, and also CMB lensing. So those are sensitive to the large scale structure. Right, so cross-correlating these with HSC data will give some more, insightful science.
And Viking, Gamma, VVDS, what are they?
Yeah, so Viking is a near infrared survey, which is shown as a light blue. Yeah, so this is designed to match with kids' depth. So this uses the same telescope as kids, and but they are near infrared surveys, where HS is optical, and plus like G and Y. So this is a shorter wavelength side on the near infrared. But adding Viking, so we can go beyond that. So that will give a better estimate for the redshift. Yeah, Gamma and VVDS is a spectroscopic survey. So yeah, they can be used for like calibration of the photometric redshift. So anyway, yeah, so this is our measurement. So we use the both spectroscopic galaxy sample as a tracers. So it has more than 8,000 square degree coverage. And we divided that into 3 redshift bins, as I show here. Like this is called low Z, and the CMAS 1, and the CMAS 2. And also we applied a luminosity cut to create volume limited samples. So volume limited samples is a kind of jargon here, maybe. So our model doesn't assume the redshift evolution for each subsamples. This is normally the case for other analysis so far as well. But anyway, so we want to make sure like the galaxy properties doesn't change within this redshift bin. So for that, we apply the luminosity cuts. So this is, again, very conservative choice of the tracers, because we use just 1/3 of the entire both spectroscopic galaxies.
So just to clarify something, when you say you use just 1/3 of them, do you mean 1/3 of them in the region that overlaps with your 140 square degrees?
No, well, the one overlapping with 140 square degrees is much smaller.
So for the delta G bit, you use all 8,000 square degrees, and then for the delta G delta M bit, you're only using the 140.
Right. Yes, that's right.
So I guess you're also assuming the bias is the same over the whole sky, which probably makes total sense.
Yeah. Yes, and also for HSC year 1 sample, we use as sources for measuring the weak lensing. And so this is 140 square degrees, as I said. And so we applied a very conservative redshift cut. So we chose the galaxies above a redshift of the 0.75, roughly same. Well, there's more as exact definition in the paper. But anyway, so we made a very conservative cut. We made sure almost all the source galaxies are behind the tracers. So this is a very conservative measurement. And so as a result, the number density of the source galaxies, that was 22 galaxies per square arc minute before the redshift cut, And after the cut, we got the 8 galaxies per square millimeter. So this is a measurement we got on the right hand side. Galaxy lensing and galaxy clustering signals. This is what we measured. So as I said, like a cosmology analysis has been often limited to the large scales to avoid the theoretical systematics. For example, like DS year one, they use the signals above 8 megaparsec for the clustering and 12 megaparsec for lensing. And for year 3, I guess they use the 6 megaparsec for clustering and 8 megaparsec for lensing. But anyway, like they are limited to the small scales. But we wanted to use the smaller scales, as I said, compared to them. And then when we try to do that, we have to model the nonlinear regime.
Can I just ask something quickly? Will you be defining WP and delta sigma at some point, or if not, can you define it now?
Right. So this is delta sigma is a galaxy lensing signal. So this is a weak lensing distortion times so-called lensing kernel. So a weak lensing signal, I mean this distortion, it depends on like a foreground structure and also configuration of observer and foreground structure and the distant universe. So the weak lensing distortion is a mix of that geometry and foreground structure fluctuation. So this delta sigma just tries to get the foreground structure fluctuation part.
And then the WP in the bottom one.
Yeah, WP is a projected galaxy correlation function. So yeah, you can measure 3D galaxy correlation functions and then integrate that within 100 megaparsec along the line of sight. So this is a WP. So we want to go to the small scales. And for this, we need to model a nonlinear regime and a galaxy halo connection. So those two stuff is a very, difficult part when modeling the signals down to smaller scales. And so we constructed so-called emulator-based halo model. So this is a combination of the emulator and the analytical HOD. So this is the schematics of our model. I will go into details of each, like dark emulator and HOD, but let me explain the big picture of our model. It starts with input cosmological parameters. And then if we take cosmological parameters, dark emulator can give a prediction for the correlation function in a nonlinear regime in a few percent accuracy. So by using dark emulator, so we can get the halo correlation function, autocorrelation function. And this is a halo matter autocorrelation function. And then after that, we analytically convolve HOD. This is an analytical model for how galaxy populates a dark matter halo. And then if we convolve that, this halo part is converted to the galaxy part. So this is the galaxy matter correlation function, galaxy correlation function. And then after doing 2D projection, we can get these observables. So this is a big picture of our model. And then the dark emulator, let me explain a bit more details. So modeling the accurate Xi-HH and Xi-HM. So this is, again, as I said at the beginning of the talk, so this enables us to predict the very accurate nonlinear correlation functions without running the n-body simulations. So what we did is run n-body simulations under 101 sets of cosmological parameters. So we have these cosmological parameters. And this right figure, shows how we sampled a combination of the cosmological parameters. Then we run the n-body simulations and then measure correlation functions, Xi-HH and Xi-HM. So this is a function of cosmological parameters and also separations. Then we interpolate the correlation functions across the cosmological parameters and using a Gaussian process. Plus, well, PCA, where I did not write this down here in the slide. But anyway, right. So this is a machine learning oriented approach to model this correlation function. And then we achieve the accuracy better than 2%. Actually, so this is published as a separate paper, as I said, like Takahiro Nishimichi, shown here, and the student Yosuke Kobayashi. He is now a postdoc at University of Arizona. They both developed this dark emulator.
How much ambiguity is there in the definition of a halo? Like, is there like a minimum mass that you have to set?
So in this dark emulator, so we use the spherical overdensity of the dark matter particles. And also there's another way to define halos, like a friend of friend, collecting particles closer to each other. So we are using spherical overdensity halo definition. But we also tested our method against mock measurement based on friend of friend definition. Yeah, and we found that there's some difference, but that difference does not affect our cosmological parameter.
And do you set a kind of minimum halo mass to kind of be aiming at the halos that would have the galaxies that HSC is observing?
They are able to provide these correlation functions down to 10 to 12 solar mass.
And up to the most massive halos that one might expect.
Yeah. And so next is how to model tracer galaxies. So we can provide a correlation function down to 10 to 12 solar mass, but not necessarily both galaxies reside in such small mass halos. So we have to model how the both galaxies populate dark matter halo for a given mass. So this is a part to model the galaxy halo connection. Yeah, for this we use HOD, halo occupation distribution. So the idea is like this, like on a right figure. So for a given sample, you can define at which halo mass that sample is likely to occupy a dark matter halo. So we first divide HOD into central and satellite galaxies. So central is supposed to be the center of the dark matter halo. And then for this HOD, so this means like for the 10 to 13 solar mass dark matter halo, there is likely about 30% of the dark matter halo has a both galaxy, for example.
Yeah, and almost none of them have a satellite as well.
Yeah, almost non-satellite. And if you go to the higher mass, they start to have satellites. Yeah, and then total HOD looks like this.
And by definition, you can't have more than one central. So that's why I guess it becomes a horizontal line at one.
Right, that's true, right. That saturates around maybe 2 times 13 solar mass, right. So this HOD has been successful to model the galaxy clustering signal so far. So we adapted this HOD scheme. But this HOD is described by 5 parameters. In other words, we have additional 5 parameters per sample in addition to cosmological parameters. So that marginalizes our limited knowledge to the galaxy populations.
I guess a skeptical observer might want to ask how one knows this is correct. I guess in your second bullet point, you say details and extensive robustness tests can be found in another reference. So perhaps the details in there. But I guess the halo stuff one might trust quite well because it's just gravity, right? Whereas at this point, you're also talking about how does one know how galaxies populate halos? So how does one calibrate this orange and blue line in order to use this?
So what we did is we created mock signals with different formalism of HODs. We generated like 10 mocks or something with different Hello Galaxy connections. And then we checked how robust our model is. So we, as I said, we marginalize 5 HOD parameters. And then this test is to check how that marginalization works. And then if it does not affect the final cosmological constraint. So yeah, what I did is in a nutshell, we prepared different mocks with a different galaxy Hello connection, then fitted our model, and then we confirmed that we can recover input cosmological parameters once the HOD parameters are marginalized.
There's two things I would have thought one would want to do. One is that, yeah, that the cosmology doesn't depend on the value of the HOD parameters, but the other one would be that the mock data looks like the real data. Is there like a goodness of fit parameter that says that it's a good fit, that the HOD model fits the data well? Is that?
Yes. If we marginalize these HOD parameters for all the mocks, the goodness of fit looks okay.
But to the mocks, but also to the real data, the goodness of fit to the real data looks okay?
Yes. Yeah, that is shown in the paper. Well, but the one caution is that maybe I guess to the community, it might be interesting to point out that for assembly bias, so our model might not work very well. So, well, anyway, this can be discussed in a live discussion later.
Sure. Yeah.
Yeah. Okay, great. So this model is publicly available within Dark Emulator. So Dark Emulator itself is also public, but Dark Emulator cross HOD, this is also public. So you can just Google Dark Emulator and then get the Python module. Right, so as I said, we did a test with a mock measurement. And then using that mocks, we confirmed that our model is robust down to 2 megaparsec for clustering and 3 megaparsec for lensing. So we were able to push down to small scales. So this is some systematic tests for cosmological inference using our data. The top row is a baseline analysis. So we used, as I said, like 2 megaparsec and 3 megaparsec for the clustering and lensing scale cuts. Also, we fitted our model with a different scale cut. Like this 4.6 is 4 is for clustering and 6 is for lensing. And 8.12 is the same definition. So if you look at the S8, like if you compare baseline and the scale cut 8.12, you see some deviations, but we confirmed this deviation can be observed in mock data, so with a noise, so yeah, it's fine. So also we checked other things like internal consistency. So we ran our analysis without one of the tracer, and so we got a consistent result for the S8. And for other things like observational systematics, we turn on and off observational systematics, and also we use the wider players, broader players for the observational systematics, but the result looks robust. And also we added a little bit of complication to the model, our model, and then this looked okay, like off-centering or incompleteness. I mean, you want to look into the papers if you're interested in. And also we run our analysis on lensing signal measured with a different photo-Z methods. So this is also again robust.
Cool. I guess you did draw attention to these scale cuts, but it does look like, I mean, it's definitely the thing that looks curious, that people are always suspicious about the small scales, right? And when you do a more large scale analysis, the omega matter changing, you said that you saw this in the mocks as well. Is there anything more you can kind of say as to why someone who only believes that one should study the large scales because the small scales aren't trustworthy shouldn't believe that omega matter is actually closer to 0.3?
Yeah, so well, actually, okay, so to talk about a little bit of what we did is for mock measurement, like we fluctuated the mock signal following the covariance of the measurements. and then we can make a single realization with that fluctuation, right? And then we prepare like a 30 realizations of them, and then for each realizations, I run the baseline analysis. I mean, 2 and 3 scale cuts and 8 and 12 scale cuts. And then, so within the noise fluctuations, so this difference can happen in the mock data. So this can be just a statistical fluke. And also, as I said, like I won't go into details. Assembly bias can be also observed like this. But at this noise level, we cannot distinguish this due to assembly bias or just a statistical fluke. Okay, so this is the final result. Right, so on the left, I compare the HSC result, our result, with the DS year 1 and the kids 1000. So for DS year 1, we found, exactly the same setup. I mean, galaxy clustering and galaxy lens. But for kids, what we found is that they use a 3D information for the galaxy clustering. So it's not really equivalent. So we just picked up the cosmic shear and the galaxy lensing. So yeah, this is a different probe, but this is what looks like. And the magenta is a Planck. So Planck is, of course, it has a very tight constraint. So right, so this is what we have. And you can see the direction of the degeneracies are very different. And yeah, this depends on which cosmology probes you use, and also which model you use. So yeah, this also can be seen on the right hand side. So this is within the HSC. Like a blue is again result of this work, and green is a cosmic shear, which was published maybe 2 years ago. So you can see the very different degeneracy directions, right? So if we combine cosmic shear and the galaxy lensing and the galaxy clustering, which is often called a 3x2 point, this will provide us with a very tight constraint.
But you haven't done that in this plot.
Not yet. That's too much work for me. So we are doing that in the year 3 analysis next one. Yeah. And the orange, yeah, I also want to focus on this. This paper will be out, I think, next week, and this is done by a student at the University of Tokyo, and this is just using large scales of the signal. So this is more conservative. I mean, much more conservative than ours. I said that our constraint is conservative, but we challenge ourselves to use small scales. But if we avoid small scales, just using the linear bias model and using a large scale. So this is the orange.
There's one thing about the plots on the left that I remember you mentioning in the paper that I found useful, and that you haven't brought it up, so I think I'll bring it up, which is that this S8 parameter, it's like some combination of omega matter and sigma 8, and it's defined in a way that kind of fits the degeneracy direction of, say, kids or des a bit better than the degeneracy direction of your analysis. So the fact that your S8 final constraint is quite wide is not a sign of imprecise statistical stuff in your data. Like the sigma 8 parameter is actually quite narrow. It's just the fact that S8 is defined in such a way that like you're quite degenerate along it. But if you chose your own S8 parameter, your one would be narrow and des and kids would be quite wide. I thought that was quite a useful thing to point out. That
maybe, I guess it would be nice to update the definition of S8. Depending on the definition of S8, tightest constraint changes. And then for each probes and for each modeling method, that slope is different. I mean, sigma 8 and omega matter slope is different. So maybe, I guess, we don't have to stick to the S8 with the alpha equal 0.5 in the future. So,
because exactly what you're saying is kind of, it's still obvious in the S8 versus omega matter contours, right? Like the blue contour is certainly wider in S8, but it's much narrower in a different perpendicular direction almost. Yeah, like it would be interesting to see a kind of joint analysis between blue, orange, green, I guess.
Right. Yeah, I think so.
How independent is the data? Like, are they different lines of sight, the 3 experiments?
Right. So the HSC and DES, they use a completely different data set. So DES looked at southern sky, and also the tracer galaxies, they use a photometric galaxies from their observations. So this is a completely different. And the kids, so we actually have overlapping region in equator. Yeah, kids observe the equator and somewhere in the south. And also kids also using the both data, so there should be some overlap. Yeah, but again, this kids constraint, it comes from cosmic shear plus galaxy lensing, and they didn't include galaxy clustering.
So there's a little bit of statistical overlap, but it's not easy to kind of, I don't know, do a chi by eye and work out what the combined constraints would be, I guess.
Yeah, I guess for the HSC and DS, maybe one could do like just joint the likelihoods, but yeah, for kids we should be careful.
Okay, so where to next? When should we expect the year 3 data, and in what ways are you intending to kind of upgrade this analysis? What's coming soon?
Right. So for year 3 data, as I said, the shape catalog is already there. So we can measure the galaxy length. So we just started the year 3 analysis, and I hope we are quick compared to the year 1 analysis, because we already built almost all of the infrastructure needed for this 2 cross 2 point analysis. But what we really want to do is we want to combine cosmic shear and galaxy clustering and galaxy lensing. I mean, again, 3 cross 2 point. Looking at the right figure, as I pointed out, the overlapping region between the cosmic shear and the 2 cross 2 point is not so large. So after combining these, we can get much tighter constraint, we hope.
So just to clarify, the kind of contour directions of the blue and the green on the right are almost perpendicular, at least in the S8 sigma 8 one, and so there'd be, yeah, okay, that's interesting. Cool. And anything else that's coming on the horizon, or?
In addition to this cosmological constraint based on 2-point statistics, so we're trying to do the cluster cosmology using HSC optically selected clusters. So this is another project going on. And also, like, we are closely collaborating the ACT. So like we are also measuring the weak lensing signal of clusters selected by SNIF Z-bridge effect. So yeah, this is another interesting thing.
What work being done in cosmology at the moment do you think is particularly underappreciated by the community as a whole?
Let's say, okay, I have something interesting, right? It's not really underappreciated, but one direction what is interesting is going to higher redshift. So the work I did was like I used the galaxies selected by HSC at a really high redshift, like a Z-4, and then I measure the lensing signal using the Planck CMB lens map, kappa map. Yeah, and so like this, like we can measure galaxy clustering signal of, for example, Z-4 galaxies, and also galaxy CMB lensing signal at the Z-4, and then you can do the similar theoretical interpretation, and then we can go into the higher redshift. And now that we are starting to see the S8 tension, it will be interesting to know what happens at the higher redshift. So for example, some theory like early dark energy predicts some sizable difference in the power spectrum at that redshift, like a redshift between 2.5. And so the measurement I mentioned, like combining CMB lensing and the galaxy clustering of the high redshift galaxies, that can enable us to constrain these theories. But it might not be underappreciated, but people are discussing about it. But this is one of the directions we should go. Yeah.
I think by the nature of this talk, the fact that like you've only just finished the work and you're already having to be interviewed on it, you didn't have time to think about this question. So that's a good response, given that you've had other things on your mind, literally getting out a paper with a a large collaboration is difficult enough on its own. Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos, and click like to help with YouTube algorithms, and share the channel with colleagues. If you have any questions or suggestions, leave a comment. If you like this video, you might also like the one from last week with Song Huang and Alexei Liaoto on analyzing the masses of galaxy clusters using HSC data as well. They had interesting results of how they could predict the masses using stellar mass of individual galaxies. So that's a great talk to check out. And other than that, thanks Hironao for a great talk.
Thank you very much.